All Parameters by Dominic Berry, Andrew Childs and Robin Kothari, and also Rolando Summer. And Dominic will give the talk.
Yep, okay, thank you. I'd like to thank the organisers for having me speak at the conference. And this is work that's primarily in collaboration with Andrew and Robin, and also give thanks to Richard and Rolando, who I also did some of the other work that I'll be talking about here. This work was just out on the archive on Friday, so if you want to read the full version, that's it there. Okay, so the motivation for this work is coming from things like trying to predict behaviour of molecules or novel materials. So if you can simulate the quantum system there, then you can understand what its properties are going to be, and perhaps design new things. So that's one motivation for building quantum computers, that you could do this more rapidly. And another motivation, well, really this is the motivation for why you want to be able to simulate Hamiltonians, to be able to simulate these systems. Another motivation for simulating Hamiltonians comes from this idea of the Sparse Hamiltonian simulation. So this was by Aronov and Tashma back in 2003, and then that led to actually building other algorithms on top of that, instead of just trying to simulate physical systems. So there's the algorithm for NAND trees, which uses that, and also the Harrow, Hassidim and Lloyd algorithm for linear systems, and in turn that's being used for generating a lot of other algorithms. Okay, so the Hamiltonian simulation problem is essentially just solving Schrodinger's equation. So you're given some Hamiltonian, and the idea is you want to look at the time evolution of the quantum state as represented on qubits of your quantum computer, and you're given some time t, and you want to simulate it within an error epsilon. So your inputs are your Hamiltonian, the overall time and the error. And when you're thinking about how efficient these algorithms are, you want to be looking at scaling in these types of parameters. And we're interested, one of the parameters we're interested in is the error epsilon, and the other parameter is coming from the actual parameters of the Hamiltonian. So when you have these sparse Hamiltonians, they're going to have some upper limit on the number of non-zero elements in any row or column, and we call that the sparseness. And we'll also be looking at the scaling with that. There's some other parameters that you can also look at, which are, well, you can look at norms of the Hamiltonian, and you can also look at the dimension, but I'll just be ignoring that because essentially all of these quantum algorithms scale like the log of the dimension. So to give you an idea of the progression of results in this area, so essentially the obvious approach using product formulae will give you something scaling like this. So this is using higher order techniques where you can get a small value of epsilon, but no matter, a small value of delta, but no matter how small the delta is, you're still going to get d to the 4 scaling there, and you're going to essentially have polynomial scaling in the epsilon. Now, these more advanced methods, you can use quantum walks, which can get you strictly linear scaling in the sparseness d, but that's at the cost of worse scaling in the error epsilon. A different approach can give you well, it's better scaling in d than that, but still not as good as quantum walks, and it gives you a logarithmic scaling in the allowable error epsilon. And essentially the new work that we're presenting here is using a combined approach with ideas from both of these approaches, which gives you the best of both worlds. It gives you something which is close to linear in d, and it gives you something that's going a polynomial in the log of epsilon. So just to reiterate, that's our main result for the complexity up there. Now I'll just explain a little bit more about what that polylog factor is. So if you're looking at queries, which I'll explain in the next slide, then the polylog factor is a log over log log. So it's slightly less than linear in the log of 1 on epsilon. But the gates is number of gates you need somewhat more than linear in the log. And we also have a lower bound, which is so the polylog here is essentially this polylog, but it's what we have is a dH max t plus a polylog, so rather than a times a polylog. So we proved that if you're looking at scaling in dH max t on its own, then it's optimal, or if you're looking at scaling in that polylog factor on its own, that it's optimal, but maybe there might be some possible improvement in terms of the overall trade-off between the parameters there. Okay, so, actually, something I was meaning to mention at the beginning, I've also posted this on the presentation on my website, so if you want to download this at any stage, you can go to my website and the file's there. So the model of sparse Hamiltonians is essentially looking at the Hamiltonian represented in some basis, and it has mostly zeros, but it's got a few non-zero entries, and in this particular example it has no more than 2 non-zero entries in any column or any row, so the sparseness D is equal to 2 in this case. Now the queries which I was mentioning, these queries are essentially a algorithm for calculating the positions and values of these non-zero entries. So for example, if you ask for the 4th column and the second non-zero entry, then the queries will tell you that the second non-zero entry is in this row and that its value is given by this. So the relatively obvious method of doing these simulations is essentially to divide your Hamiltonian up into a whole lot of Hamiltonians which are easily simulated. So in Seth Lloyd's original work, the idea was that these would be interaction Hamiltonians, and you can also use a similar approach with the sparse Hamiltonians where you have a decomposition into simpler Hamiltonians. And then you can just divide your time up into many short intervals, and in each short interval you can use a product of exponentials of those individual Hamiltonians. And that will, this is essentially the simplest type of product formula, and you can also use better product formulas that give you better accuracy, but they still generally have restrictions on how well you can do, no matter how cleverly you design these product formulae. So with the more advanced methods, where there's a range of ones that I'll mention here. There's the compressed product formulae, the implementing Taylor series, which essentially gives similar results as the compressed product formulae. Also quantum walks, and they then go from quantum walks to the new idea, which is essentially a superposition of steps of the quantum walk. So I don't have time to talk about these ones in detail. I'll just try to explain the central ideas from those works which we use in the new work. So the crucial ideas for the compressed product formulae are to break the overall evolution into segments. Then in each segment you want to use controlled operations which are going to succeed with a certain probability. And then the third thing is to use oblivious amplitude amplification to turn it from a probabilistic thing to a deterministic thing. So the idea with the segments is essentially you have just your overall time. The evolution is just broken up into a whole lot of segments, and then on each segment you want to have that Hamiltonian evolution that is over time t divided by r, and I'll be using r for the number of segments throughout this. So then to do things with control qubits, the simplest one is if you just have a U which is self-inverse, then you can have a control qubit which you use some operations to put into a superposition. Then you have a superposition of either doing the identity or doing that operation U, and provided you have the correct measurement at the output, you actually get evolution under that unitary U as a Hamiltonian. Now, of course, with real Hamiltonians, you can't rely on them being self-inverse, but you can break them up into self-inverse things. And in this approach, we used compression to turn this into a rather more complicated procedure, but the central idea is still that we have something which is controlled operations on a segment, and then there's measurement at the end which you would want to give you all zeros to have success of that segment. Except then the idea with the oblivious amplitude amplification is essentially that we replace the measurement with doing amplitude amplification. And the oblivious part of it is that it's only acting on these control qubits. So essentially the idea in the simplest case is that you just want to reflect on those control qubits and then run the entire procedure in reverse, reflect on the control qubits again, and you run it forwards again, and then you get success. And the neat thing about this is it's only reflecting on the control qubits. You're not touching this target state at all. And that's very important because you're doing this many, many times. You have to do this for each segment. And if you were touching that the target state, then you wouldn't be able to do that. Okay, so that's the first one. And I'll next say a bit about the idea with using Taylor series. And I should mention that was just out on the archive last month. So the idea with Taylor series is essentially, rather than thinking of doing things in a product formula, you're just thinking of saying in each segment you represent your exponential as a Taylor series. And the general idea is, well, if you just ignore for the moment the fact that the Hamiltonian isn't unitary, if you could perform the Hamiltonian to some power and you had a control register which gave you a superposition over K, then you could get that evolution under that Hamiltonian. So that's the general idea, and to actually do this, you need to expand that Hamiltonian out as a sum of unitaries, and then your exponential is going to be a rather more complicated thing with products of these unitaries. And then you can actually perform this using a more complicated control registers and a controlled unitaries here, and that will give you the evolution under the Hamiltonian. And again, you can replace that measurement with a oblivious amplitude amplification. So that's the Taylor series, and next I'll talk about the quantum walks, which is a little bit older work, but it's more directly related to the approach that we use here. So of course you have the standard quantum walks, which would be using a position and coin registers and alternating the coin and step operators. So we don't use it in that form. We use a rather more complicated one invented by Segedie, which is, rather than using something which is very asymmetric with one thing which is infinite dimensional and one thing which is a qubit, so you're using two subsystems with arbitrary dimension. And in our particular application, we want these to be of equal dimension. And then that step, rather than being something like this, it's actually a controlled reflection. So how that works is a controlled reflection is essentially taking for each the basis state J on one of the subsystems, it's doing a reflection about a particular J-dependent state Cj on the other system. So in our application, after doing that, we want to swap the two systems and do this again. And more generally, you could imagine doing different controlled reflections, alternately controlling on each system. So what we have is an overall step operation, which is this controlled reflection followed by a swap, and we also put in an I factor, which makes things a little bit neater. And I should also mention that we want to have a controlled preparation, which is just preparing Cj based on J in the first system. And if you can do this controlled preparation, then you can use that to build the controlled reflection. So essentially all the difficulty here is in doing that controlled preparation. So given that, the overall simulation of the Hamiltonian evolution using these quantum walks is basically using two copies of the Hilbert space, which is indicated by the circles here, and you start off with the state in one of these subsystems, then you use this controlled preparation to essentially map it so you have it jointly over both of these systems. Then you perform a whole lot of steps of the quantum walk according to U, which I had on the previous slide, which is again jointly on both of these systems. And then at the end you invert the controlled state preparation so everything is mapped back to the original Hilbert space, and you want to have the final state in that original Hilbert space. So remember this T and this U is dependent on T, and that T is using a state which is dependent on the matrix entries of the Hamiltonian. And we can actually do that using order 1 calls to the Hamiltonian. So if you're thinking about the complexity of this thing, it's really just going to be how many steps of this walk you're using. So the reason why you can use this walk is because it has eigenvalues that are related to the eigenvalues of your Hamiltonian. So if you're starting with eigenvalues lambda, then your step is going to have eigenvalues which look like this. So it might seem a bit strange to have 2 there, but essentially what happens is that one eigenstate of your Hamiltonian under that initial operation T, that's mapping to a superposition of 2 eigenstates of the operator U. Now, in comparison, what you actually want is a phase factor like this. So if you think of first of all, assuming that you can distinguish between the plus and minus here, you can correct to a step UC which has this value, and then you can see that essentially the difference between these two, well, this doesn't have a T in it, of course, but the difficulty is that you have a lambda here, but you have a nonlinear arc sine lambda here. Now, if lambda is small, then because of the arc sine is close to linear for small values of lambda, it's going to be reasonably accurate, but it still doesn't give you something which scales very well with the error, because you would need to take this lambda to be smaller and smaller to get more accurate simulations. So the idea in the new work is, rather than just using a single step, we want to have a superposition of different numbers of these steps. So rather than just say having it from a superposition over positive powers, we're going to have superposition over negative powers in a fairly symmetric way. So of course the negative powers, it's just going to be Hermitian conjugate to some power. And in the same way as before, we can think of having a controlled operation where we have a register which is going to be in a superposition of different values of k, and that's going to control how many of these UC operations we do. And then provided we get the correct measurement result at the end, then we're going to get that superposition operator U. Now, as you can imagine, if you're thinking of, say, an expansion of arc sine, this is going to be linear to first order, but then it's going to have higher order terms there. And if you have a superposition of things with different powers, you can imagine choosing values of alpha k which are going to cancel out those higher powers and make this thing more linear. So that seems to be quite a difficult problem, but it turns out this is nicely related to the properties of Bessel functions. So essentially we're trying to find values of alpha like that, and if we rearrange things, we find that that phase factor we want is given by this, but then that's just a generating function for Bessel functions. So if you take an infinite sum over jk's times mu to the k, then that's actually equal to that expression. But that's just the form of what we wanted, so except this thing has a cutoff k. So because the Bessel functions drop off quite rapidly for large values of k, that means we can essentially just take these alpha k to be Bessel functions. Now that seems quite neat, but it's even neater because so far I've been assuming that we're using some corrected step which would be requiring us to distinguish between the plus and minus subspaces of that operator u. Now, it turns out that if you assume that you haven't distinguished between them and you're just using the uncorrected operator u, then you would replace all of those mu's with mu plus or minuses. But then when you look at this expression on the right has the mu plus or minus, but that should be a mu plus or minus on the left there as well. But the coefficients that you need don't depend on that plus or minus. So it turns out that you don't actually need to distinguish between the plus and minus. You can just use the same coefficients regardless. So that's just reiterating that. So then to go over the complete algorithm and bringing all of these things together, we first of all start with the doubled Hilbert space, and we want to use that T operation to map our state into that doubled Hilbert space. We divide our time up into R segments, and that R actually needs to scale like dH max T. And then for each of these segments, we want to use this superposition where we have each of these UKs performed with a weighting given by Bessel functions. Now, instead of using those measurements, we instead use amplitude amplification, which enables us to do each of these steps deterministically. Then once we've done all of these segments, we just need to map back to the original Hilbert space, and we'll have our desired final state in the original Hilbert space. Now, the total complexity of this thing is going to be the number of segments, which is this dH max T, times the complexity of each segment. So we have that dH max T, and the complexity of each segment is going like K, which was the cutoff on the number of these the U operations that we would do in each of these steps. So the next question is, how do we choose that value of K? So that just comes from the properties of Bessel functions. So you can bound Bessel functions in this way, and that's essentially just like the bound for the error terms in a Taylor series. And it means that you can choose the cutoff K to be polylogarithmic in 1 over epsilon, and that means it's log over log log, which is where that factor comes from. So then our overall scaling is that dH max T times the polylog factor coming from K. So that's one way of doing things in that we've used a whole lot of short segments with a high probability of success on each one, so we don't actually need to use many steps of amplitude amplification. A different approach would be, well, you can think of using one large segment, or perhaps some intermediate sized segment. So if you have one large segment, then you would actually be using coefficients which are given by Bessel functions with a large argument given scaling like dH max T. And this is a rather complicated thing, but it is fairly efficient to evaluate classically. And then the neat thing about it is that it goes up to dH max T, and then it has a polylog sized tail on it. Thanks. So that makes it look like you could manage to do things with a complexity which would be a dH max T plus a polylog factor rather than times a polylog factor, until you take into account that you actually need to do that amplitude amplification there as well. And that would give you an extra factor scaling like the square root of dH max T. More generally, if you choose segment sizes like tau to the alpha, and I should mention again that tau is equal to this dH max T, and take values of alpha between 0 and 1, then you would get scaling like this. So as you take alpha to 1, then that's tau to the power of 1.5, which is slightly worse, but the factor that's multiplying the log 1 over epsilon would just be root tau, which is a slight improvement in that way. Now, I'll just finish off by mentioning how you go about proving the lower bound. So we also have a lower bound saying that we have, you can't do simulations with any better than efficiency any better than the sum of those two terms. So the general idea is looking at something which is kind of like a rotation. So if you look at the picture of the Hamiltonian where each node is indicating a state and each connection between a node is indicating a non-zero element in the Hamiltonian, so that all these nodes which are connected are things which you can get to by evolving under the Hamiltonian. So when you choose the Hamiltonian appropriately, then you can start with a zero state and evolve it for some time and get exactly to the state n. Now, this is on its own, it's not something you can use to prove lower bounds. What you need to do is actually make two copies of that line and then swap between them according to the bits of a bit string. Now, it turns out that you can't evaluate parity of a bit string any faster than linear in the number of bits there. So then with this, if you evolve under the Hamiltonian, you're just going to go along one of these lines, and you're not going to swap from one line to the other. So you're either going to go along that red line or go along that blue line. So if you start on the red line, you're going to get to the end and have n in one of the registers and have something telling you the parity in the other register. So what that tells you is that you can't do simulations with efficiency any faster than h max t with that approach. So to put the sparseness in there as well, what you can do is just take many copies of each of these lines. And so in this example, it's just 4 copies, and you start off with a superposition over these 4 initial states. And as you evolve it, you're going to keep being in that equal superposition on each of these nodes. And at the end, you're going to be having that parity in that register again. And the neat thing about this is that the D copies boost the strength of this thing essentially by a factor of D and tell you that you have a lower bound of DH max T. So that's how that's found. Okay, so just to conclude here, what we've shown is an algorithm which gives us complexity for Hamiltonian simulation, where we have sparseness times the max norm of h times the time times a factor which is polylogarithmic in the allowable error epsilon. And we've shown a lower bound which is scaling almost like that. So it's the scaling close to linear in dh max t, and it's scaling polylog in the error, but there's a plus there other than a times. So it is conceivable that there might be ways of obtaining further improvements in these algorithms. And the method we've used is essentially combining the approach of a quantum walk and a compressed product formula approach. And I'll just reiterate, this is on the archive, and that's the archive number there. Thank you.
Okay, thank you very much. So we have time for a couple of questions. Okay, so I guess a question I have that you alluded to at the end is, which one do you think is right, the upper bound or the lower bound? Like the times polylog or plus
Well,
polylog?
neither of them are right, because
Right, yeah.
we have a lower bound actually, which I didn't mention here, which is slightly larger than this. And we also have we have the other approach which I mentioned here, which gives a slightly different scaling, and for some values of the parameters that's going to be less than for the scaling which I've given there. And sort of I'm hopeful that maybe there might be some way of trying to, essentially if you think about this, that's the overall weighting on the number of the steps that you want to use altogether. I'm thinking that maybe there might be some way of using shorter time steps, but still correcting for having the right weighting there. But I haven't managed to get that approach to work yet.
There's a question over there.
Hi, I have one question. So the sparsity depends on the basis that you choose to represent the Hamiltonian. So how do you choose it?
Typically, there's going to be some obvious basis, and though in some cases there might be something which is a sum of things which is sparse in two different bases, which this type of approach doesn't work so well. But in most cases, the sort of the basis that it's going to be sparse in is going to be problem dependent, and it should be reasonably clear.
Okay, thanks.
Okay. Any further questions? Okay, well, if not, should we thank Dominic again? And now we have a short coffee break, and we restart at 4:10.